here we have it where this we have this curve, and we have that it's defined for y being greater than 0. And the first thing they want us to do is they want us to find dy dx. They want us to differentiate this curve. We're going to use implicit differentiation in order to do that. Once it is that my writing pad turns on. There we go. Okay. So they give us the actual value that we need to get to. So we can check our answer and make sure that we are correct. So I'm going to write the curve. The curve is y squared minus x squared times y equals 6. And what I have here is I'm going to use implicit differentiation. The derivative of y squared is 2y dy dx minus, now here I have to use product rule. This is a product x squared times y. It's 2x times y. The derivative of x squared is just 2x times the other function, and I want to put this in parentheses, plus the derivative of y is dy dx, and then times x squared equals, the derivative of 6 is just 0, it's a constant. Now I want to solve this for dy dx and make sure it matches this here. So I'm going to get 2y dy dx minus 2xy minus x squared dy dx equals 0. Now I add 2xy over to the other side. I'm going to get 2y dy dx minus x squared dy dx, because I want to get all my dy, any term with a dy dx on one side. So I keep these two, right, and I add that other one over to the side, 2xy. Here I can factor out a dy dx to be left with a 2y minus x squared equals 2xy. And now I've shown that dy dx, after I divide on both sides by 2y minus x squared, 2xy, 2y minus x squared. And I'm done with part A. Now they want to write an equation for the tangent line to the curve at the point 1, 3. So the equation for the tangent line involves me finding the slope of that tangent line. The slope of the tangent line is given by the derivative dy dx. I have an expression for dy dx. So dy dx, the slope of the tangent line, when x equals 1 and y equals 3, again, this is slope of tangent line. I plug in 1 for x and 3 for y. I'm going to get 1 for 3. 2 times 3 minus 1 squared. I'm going to get 6 on the top. 6 minus 1 on the bottom is 5. And I have slope and I have a point. An equation for y, the tangent line could be y minus y1 equals m times x minus x1. This is point slope form. And I get y minus 3 is equal to 6/5 x minus 1. I can add the 3 over the side to get the final thing here. When I add the 3 over the side, bear with me, I'm moving up to here. 6/5 x minus 6/5 plus 3 is going to be plus when I distribute here, I'm going to get the 6/5 x minus the 6/5, right? And then I'm adding 3. So it's going to be negative 6/5 plus 3, which is 1 4/5. And then that's 5, 1 9/5. Is it in slope-intercept form? But I think they accept it if I just added 3 over here. And I could say y equals 6/5 as x. 6/5 times x minus 1 plus 3. And I think that that's okay as well. But either or, we got b. Now, show that there's a point P with x coordinate 0 at which the tangent line to the curve at P is horizontal. Find the y coordinate of P. Okay, so I want the derivative to be in 0. Show that there's a point P with x coordinate 0 at which the line tangent to the curve at P is horizontal. So basically what you have here is that you want to find the y coordinate, but you know that if x is 0, the slope is 0, because you're going to get 2 times 0 times y, whatever y is, doesn't matter, you're going to get 0 on the top the moment x is 0. And then you're going to get a 0 over here, but 2y might not be 0. So you're going to get 0 over 2y, which is 0. So the moment x is 0, the slope is 0, and the curve is horizontal. So x is 0, the curve is horizontal. Now we need to find the y coordinate. You plug in x to the original curve, and you plug in 0 for x. Sorry, you plug in 0 for x in the original curve, and you solve it for y. This is going to be 0 squared times y equals 6, and you get y squared. This is 0. 0 squared is 0 times y is 0 equals 6. Now this gives you two values for y, but what gives it away is that this is the y coordinate. The positive one is that y must be positive. Now we gotta find the second derivative of this function, and they have right here, they have already dy dx equals 2xy 2y minus x squared, and what you need to do here is quotient rule. So it's you need to take the second derivative. This is the notation for differentiate the derivative of the derivative. And what I have here is quotient rule, and I'm going to have to use product rule inside of that and so forth, but let's see. So it's going to be equal to the derivative of 2xy, the top function, times the bottom function. Minus the derivative of the bottom function times the top over the bottom function squared. Now, let's look at these things that I need to find the derivative for. I need to find these pieces here. So these pieces, I need to find the derivative of 2xy, right? The derivative of 2xy, it doesn't matter whether you take, you put the 2 at the side. I'm going to do this times this as product rule. So the derivative of 2x is just 2 times y plus the 2x stays times the derivative of y is dy dx. And now I have y prime, 2xy prime, and I write that in 2y plus 2x dy dx times 2y minus x squared minus, and now let's find this. So the derivative of 2y is 2 dy dx minus the derivative of x squared is 2x. And I write that in there, and I get 2 dy dx minus minus 2x times 2xy over 2y minus x squared. And what you can do is, as a final step, and I leave it to you guys, is that you could write dy dx. So everywhere we see dy dx in our second derivative, so we have dy dx here. This is d2y dx 2. Okay, it means the second derivative of this original curve. And if you see again, so now let's go back. I have dy dx over here. Instead of writing that, you could actually write what you have for dy dx. You could write this here. So instead of writing this, you could write that expression in both of those for dy dx.